the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to another episode where today we have the history of physics, episode number 84. And today we actually have, in my opinion,
Another banger.
another absolute banger. Like you can't really get better. I mean, it always just does. But so today, you've already read the title, of course. We are talking about Stephen Hawking
Oh,
and Carl Friedrich Gauss.
let's go. Crazy figures, monumental figures in the world of physics.
That's what I was just going to say. If you're in any like form of physics, math, you have, Hawking, the world has heard of him, also because he's very recent. So Hawking, I guess, is a little bit of another story. But with Gauss, I could see a lot of not like average people not really knowing who he is, but listeners better know him, better enjoy what we have to bring today's episode.
And a little story, I think I've said this before, 100% I've said this before, but on the day that Dr. Hawking died, I was in the Greenwich Observatory.
Yes, yeah, you did.
In London, yeah.
He passed
was
away
there.
on Pi Day too.
I was there, yeah.
which was great. He passed away on the day that Einstein was born.
Einstein was born, yeah.
It's
Isn't
pretty
that
cool.
the same thing with somebody else?
Yeah, no.
Like
There's something
somebody else
with
before
Einstein, too.
Einstein has like died on Pi Day.
There is someone
like
else
that.
famous that has, because I remember like a Pi Day thing was pretty famous when Stephen Hawking passed away. So there was this whole thing. Anyways, also you may have listened to our quick message that we released on Spotify yesterday. On all our listening
If
platforms.
you're listening to this right now, it's no longer up. I'm gonna take it down.
Oh, you're gonna take it
Yeah.
down? Okay. So it's no longer up but it was basically just because, again, we have a lot of school nowadays. So I'm just letting all the listeners know, all the viewers know. We have a lot of school coming up. We have our midterms. I mean, basically the whole semester is midterms. It's just a lot of work for us.
Yep.
So even an hour and a half. Remember, the podcast is not only an hour and a half. It's also like research. It's also taking away time. It's a lot of stuff that we also have to prepare for it. So, sometimes it does get in the way of stuff. So we're obviously going to be trying our best to be sticking to the Monday 12 p.m. schedule, but there may be exceptions. So I'm just letting you know, we will be posting all our updates on Instagram like we always do. I believe I sent out a YouTube post yesterday as well. So we're going to continue to do that. But, just keep up to date if you're like, oh my God, where's the episode? It's coming just a little bit later. Just a little bit later. So do we have any news for our listeners today?
Go right ahead.
Today, we have quite a phenomenal metric. I actually am, one second, with the news. Wait, sorry. Oops.
You're clicking on all the wrong buttons.
I clicked the wrong one. No, because I thought you were going to do comment of the week and then I was going to transition into news. But sure, we can do this. Kind of put me on the spot there, Parker. Thank you. But we're at 280K downloads.
Damn.
Crazy. Thank you to everyone who continues to follow, continues to download our podcast episodes. On YouTube, we're almost at 1,000. We're at like 1940.
You mean 2,000?
Yeah, sorry, 2,000. We're at 1940. So keep it up. Thank you to everyone who continues to subscribe. That's basically our big numbers are for Spotify. I don't believe
we're almost at 16,800 followers.
Nice. That 20,000
crazy.
will be a
20,000
big
is going to happen, by the way. It's been mathematically guaranteed to happen before New Year's.
I hate the
Insane.
word guaranteed, but sure.
Insane.
But sure.
Absolutely crazy. So remember to follow the podcast wherever you're listening to this, and also come on YouTube, subscribe, leave a comment. And why should they leave a comment?
I was just going to ask you, Parker, why would someone just leave a comment on a podcast?
Because every single week we pick a comment and we call it the comment of the week. And
that's crazy. That's such a good idea.
This week's comment comes from Hari. So started to listen to your podcast when episode 11 or 12 came out. Crazy OG listener.
Wow.
I found this podcast on Spotify while trying to find some good podcasts to listen to while drawing. Started to listen while I was in 10th grade. parentheses, learned a lot of stuff related to math and physics. All the best from India.
Awesome.
Thank you so much
Thank
for
you,
your
Harry.
comment. And make
Great-
sure to
great comment.
leave a comment on this week's episode. And next week, we might just pick your comment to be the comment of the week.
One thing about comments I do want to mention, you might be wondering, where is the giveaway for World Scientific? Just a quick little mention.
Yep.
A quick little mention. Have not forgotten about it whatsoever. It's still coming up. Just a small communication issue that's happening on both parts right now.
We have picked the winner, but we can't announce it yet. So,
Yeah, exactly.
So we're gonna figure this out.
Yeah.
We're gonna get the book out to the winner, and we're gonna announce the next one because we got 10. We have
Yes.
10. So
Oh, we kind of. I
Yeah.
don't know if we told anyone that.
No,
but
we
yeah,
did.
have
We
10.
did.
Oh,
We
we
did. Yeah,
did.
for
Okay,
sure,
yeah.
for
So
sure.
we have 10 different books. So yeah. So don't worry about that. I mean, if you have commented, don't worry. It's still there. Again, the winner's already been chosen, so like, there's no real point. But just letting you know to keep your hopes up because someone's gonna win.
okay.
Okay, let's just get into it. Let's just get into
Boom.
maybe the craziest podcast.
We're gonna go back and forth
Yeah.
like last time.
Like last
between
time.
the two
I think a nice
to keep-
history of physics.
to keep the neurons jumping around, keep the connections going. So
How about we start with Carl Friedrich Gauss?
Johann Karl Friedrich Gauss
Jeez, this guy had to do that.
from Germany. He's from
Okay,
Germany.
so you had to do
Yeah,
that.
I had to.
For sure. For sure.
Born in 1777. Now, get this. April 30th. But why is that such a crazy thing? Here's why. Because when he was born, his mom actually was illiterate. And she never wrote down his birth date. But she remembered one thing, that he was born 8 days before this celebration. I think it was like a religious celebration.
Okay.
And that celebration happens like 40 days before Easter or after Easter or something like that.
Oh, so they kind of.
And Gauss himself calculated his birthday. No,
Imagine like being 15 years old. Oh, when was I born?
he came up with an algorithm to like calculate dates in the past and the future. Like, those people who say like, oh, what day were you born? Oh, you're born on a Tuesday, whatever. Like
Those crazy guys. That just
like
know
those
every
guys
day.
that just connect like the numbers to the month to the day of the week.
It's
and
all just an
like,
algorithm in
Like
their head.
he made it.
Oh, he's the one that made it?
Well, he made like one
Or
of.
he
I don't know.
probably
I
made
don't know
an
if it's like
algorithm for himself.
He
Yeah,
made
yeah.
he made a algorithm
Yeah.
that calculated his birthday. The birthday was on a Wednesday, 30th of April, 1777.
Wow.
So, if that doesn't give you an introduction to Carl Gauss, I don't know what does.
That's definitely interesting.
He's one of the craziest, not as in good, mathematician / physicist / astronomer that has ever lived. He's like one of the greats. Last time we talked about Euler's mostly a mathematician, or did he do physics also?
Euler was mainly math. Euler was math.
Yeah. Well, Gauss is up there with Euler. He's done a lot of stuff. But back in, this sentence, I feel like goes for any possible time period. But I was about to say that back then there was a lot of stuff to discover. So
It's true.
This
It's
is
true.
just true for. It feels harder when it's yourself living in the present. Like, oh, it's so hard to discover things. But this is just everybody.
No, but I mean, obviously, it also like the whole thing with, oh, they didn't know this. Like that whole
Yeah.
idea is so skewed because obviously in that time you just had a different understanding of things. Like we've understood it like that's our fundamentals, so we can be like, okay, let's continue. But for someone
Definitely.
literally inventing this, it's completely different.
Definitely, it's just you're just in a dark room, just reaching around for things.
But Gauss is seen not only in math but like crazy.
No,
in physics
yeah,
too.
yeah,
That's what
physics,
I'm saying.
physics, yeah.
And but also math. Like
Yeah, no, I know. Also math.
He's a big guy in like two very respective fields. So physics, it's mainly thermo, right? That he's in.
No, electromagnetism.
Oh, what am I saying? Gauss's law.
Yeah.
That's not thermo. Sorry. Yes, electromagnetism, and then math. Obviously,
Mostly
comes with
just
statistics.
magnetism though, but yeah.
Yeah, because all of Gauss's stuff has deal with that. That's cool. So maybe we can transition on to a little biography.
Well, hold on.
Continue.
I just wanted to say a couple more things. So Gauss was like, he was that smart guy in your class when he was a kid, who just like knew everything. He corrected a math error his father made when he was 7 years old.
Wow.
Sorry, 3 years old.
3 years old.
My bad. My bad. 3 years old.
That's crazy.
When he was 7, he was able to solve like these crazy problems that nobody should be solving when you're 7 years old. Listen, if you've been to a math class, then you've a university math class, you've probably heard this story before, because the profs loves to tell it when you do series and stuff. They love to say this, but if you haven't heard it, this is a good time to say it. When Gauss was in school, a punishment that the teacher would make the kids do when they did something stupid would be to add up the numbers, the integers from 1 to 100, and then write it out, write the answer. And when you write the answer, like, okay, punishment done, Obviously, if you were to add 1 plus 2 is 3 plus 3 is 6 plus 4, it gets, once you get to the double digits, it gets a little tedious. But Gauss was smarter than that.
He figured out.
He was beyond that.
Of course he did.
He was like, wait, 100 numbers. That's an even number of numbers. What happens if I split down the middle, right, at 49, between 49 and 50? Is that how it works? Or 50 and 51?
And 49.
Yeah, 51. Anyways, what happens is that you flip one of them, like you reverse the order, and then you add the 2 rows together. You know what I mean? Unit by unit. Like you add 1 with 100, 2 with 99, 3 with 98. Yeah. And those are all constant, right? Like 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 90. So now you separated the list in 2. So the 2 sections have 50 elements in them, both of them. Now you added the things together, and now you have 50 elements of each one having a value of 101. Now doing 101 times 50 is a lot shorter than adding 1 plus 2 plus 3 plus 4 plus 5. So 101 times 50 is 5,050. I came up with that answer in like 3.2 seconds. And the teacher was like, wait, well, I'm saying Carl. The teacher was like, wow, you broke my punishment by being so big-brained. You just did. And now it's a formula. If you want to add up numbers, just integers from 1 to anything, it's the final number.
The amount of numbers.
Because
you start from 1.
It's like where you stop, it's n. So n times n plus 1 divided by 2.
This also only applies when you're starting from 1.
Only from 1. When you start from 1. But you can go to any number, and that number you call it n, and the sum is just n times n plus 1 divided by 2. So, crazy.
Wow. No, I mean, Gauss definitely had like a childhood and a half. I know he has like a lot of stories with him just flexing on his teachers.
No, for sure.
For sure. I think we can...
He's probably smarter than his teachers.
We could have a whole podcast on just his stories. But transitioning on to our other guest of the evening, Dr. Stephen Hawking, born 8th of January, actually the same date as my father.
Oh.
I don't know why. Just cool. 1942. So this was like...
statistically,
well,
it had to be somebody's father.
You're right.
I am right.
You are right. I'll give you that. So full name goes by Stephen William Hawking, and he was born into a family of doctors. And actually, for a long amount of time, his father was pushing him to get into medicine.
That's a lot of pressure.
Because he said medicine will get you the jobs. So he's like, you got to do medicine. And Hawking was always interested in just physics. He was actually more interested in math. Originally, it was like kind of a math and physics kind of thing that he was interested in. It started, again, high school, no one really is worrying about, but in his undergrad experience and stuff where his father kind of pushed him to go to Oxford. So at that time in Oxford University, there was no reading of mathematics. There was no like applied mathematics. So what he had done, he went into a physics and chemistry degree. So he started to take basically physics and chemistry, instead of his passion for math. And he was still, obviously, math still comes up everywhere. But like he was primarily focused in that area, So he does this stuff, and after his experience at Oxford, he's like, "You give me first." Like, he was pretty confident in himself, and he kind of knew that he was smart too, because at his university, like, he was, I mean, a lot of people, again, this is just stuff that I'm getting from people places, but a lot of people said that he was kind of bored, he was lonely, because he found the work really simple, like, to understand, to go through. So his undergrad was kind of a breeze, and at the end, he was like, hey, if you give me first, I'll go to Cambridge. If you give me second, I'll stay at Oxford.
Wait, what? Second what?
Like second place, like in his class, like in his rankings. And well, he went to Cambridge for his graduate thesis, for his PhD, where he just redefined the world. But so that happened, and it was pretty funny, I think, in my opinion. Just like how he just like, hey, you do this, I'm gonna do this. I'm telling you right now, I will go to that university.
That's
and then
funny.
there he goes.
Wait, when did like the whole diagnosis thing happen?
Yeah, so that was much later. That was
much
when
later.
yes. So that was not much later, but that was in his doctoral thesis. So while he was writing his thesis at the University of Cambridge is when all that stuff happened. So I believe it was about, yes, it was, I think about, it was a couple years before he actually submitted his thesis, because what happened was interesting. Now, for those of you that may have seen The Theory of Everything, which is a great movie, by the way, it explains a lot of Hawking's personal life really well, but it doesn't really get into like the science of it. So if you want to like just know about Hawking himself, that's actually a really good movie, just to like find out about, you know, how he was with his family, how he created a family, like what his friends were like, what he was like. Like, it gives you a good gist.
But actually, like, the physics itself is in the book.
The physics
The theory of it,
is where.
theory
Oh
of
yes,
it.
of course. Yeah.
Oh wait, no, sorry, it's not
the
called a
phys-
theory.
It's in a brief
A
history of time.
brief history of time. Sorry.
So he actually not even in a brief history of time. It's pretty.
I mean, there's
Yeah. No, for
you
sure. It's more
learn
than
a
the movie,
lot.
Of course,
You
of
learn a
course.
lot.
Of course. It's a classic. But anyway, so Hawking so now I'm going to obviously focus a little more on the science part of what he actually did, of course. And Hawking is obviously known for his ALS disease that he acquired while in thesis. And obviously, I mean, we all know the story now, at least some of us that have been following him, that when he was diagnosed, they were like, well, there's no real point for you to continue your studies. They told him just to drop because he was just going to die. Like he had I believe like 2 years to death. Yeah, because at that time it was like a motor neurological disease, which is now kind of, I mean, also known as ALS. Your what do you call it? Lou Gehrig, right? The baseballer. Anyways, so it's basically it got worse over time, which is worse.
The baseball? I don't know.
The base, yeah.
I don't know.
Which is how it started. Anyways, because he got it and it started.
Okay.
So
wait, he was off
anyways,
topic.
we're not getting into that at all. We're not getting into that at all. So he gets this disease, told that he's gonna die really soon. Turns out the disease is taking longer to kill him. So he's losing functions slower and slower, right? And he's just going on with his life, even though he's told not to do anything. He's just like, well, what else am I going to do? Like, I only have these 2 years. Let me just do something. And that's when he did everything.
Damn.
Like, I mean, take in, he was told that he would live 2 years. He lived 70.
Yeah.
Like,
wait, 70 more?
Yeah, or like, cause no, he died when he was 77. Sorry. But maybe
So
like 50 more. 50.
more.
Either way,
you're
told you're gonna die in a year and you live like 60. Like either way, that's a win. So either way, that's a huge win. And anyway, so what is it that he actually did? At that time, just a quick little. We can get into Gauss too. At that time, the Big Bang wasn't really a very popular thing. There were two popular theories. The Big Bang theory, which proposed that, well, things had started from something smaller. And do remember, the Big Bang didn't really have a lot of scientific at all evidence to it, because it was just actually invented by a news reporter. He was No, of course, he was paraphrasing a scientist, but the actual science behind it was just an idea. It's like, hey, listen, what if the universe is expanding from something small because we can see it accelerate, so it had to have come from something smaller. Deducing Hubble's observations, we can get to, hey, maybe the universe started with something smaller and it's now this.
Wait, here's a quick question. If you look at any galaxy, like in the sky, any arbitrary direction, are there any galaxies that are accelerating towards us?
Yes, Andromeda.
Oh yeah.
Yeah.
Yeah, that's true.
So it all depends.
No,
on,
but like I'm talking like not in our local cluster.
because the whole point of the universe's expansion is that.
No,
the
but I
far-
know. But can you like? Is there one that's not in our local cluster, but like still accelerating towards
by
us?
the laws of dark energy and what we understand about the universe, no. Because the whole point of it is that it's like a balloon, and it's like the balloon analogy.
No,
Like
yeah.
two things, no matter how, they're always gonna get farther away, right? Unless one is already in motion, which
Okay,
is probably
wait, maybe not accelerating. What? Just like traveling
towards us. I
towards
think
us.
that's possible.
That's possible.
I think that's
Yeah, yeah.
possible. I think that's
Sure,
possible.
sure.
Anyways,
I would expect though that most of them would be like redshifted. down.
yeah, most of them are. Which and then that's what he sees. And,
Yeah,
and you
that's-
see, the farther away you are, the farther.
This is why I
and that's the
asked,
crazy. The
because-
farther away you are, the
Yeah,
faster
the-
you accelerate,
yeah.
which should not. You know what I mean? So that means that the universe is accelerating. Anyways, now this guy, Stephen Hawking, PhD, so he's doing his thesis. He's doing it in the works of cosmology and general relativity. So he has a good. He was actually called the Einstein of his undergrad, I believe. So a little interesting there, and he was. I mean, at that time, black holes were mildly understood by the general theory of relativity. It's like, hey, there is this gravitational influence on this one part of space that's infinitely curved, and as a black hole is being formed, well, the singularity, well, there's more mass that's being kind of brought into this one point, and when there is enough mass that breaks this critical mass, it's now a black hole. So he's like, wait a second. What if we reverse the process? And instead of a black hole collapsing, or a star collapsing into a black hole, what if a black hole kind of started a star?
I have
Now,
an issue with that.
That original idea was not actually what he went with.
Yeah.
What he went with is, what if we approximate the black hole to be the universe? And this is where it got crazy. Because with Roger Penrose, the original stater of the Big Bang, with like the inflationary model of the Big Bang, both of them released the paper, and he actually this was his PhD thesis actually on the universe being modeled as a black hole. And what he did was he mathematically showed the universe's starting point as a singularity. And as it expanded, he basically showed how the general theory of relativity still matches up with what we understand. So he used the field equations to basically show that the Big Bang is our most accurate model that we have today. So when people say the Big Bang is a theory, yes, it's a theory, but with what we know about general relativity, it has been proved. And that proof was done by Dr. Hawking himself.
Wow.
Yeah.
No, that's crazy.
That is pretty crazy. That is pretty crazy. Right?
Wait,
Just try to think
when
about that.
When you were talking, I was thinking about how cool black holes are, and I want to do another episode on black holes.
Black holes part 2.
But like I don't know what we talk about, to be honest.
We talked about a lot of things
We did talk about a lot
in the
of
very
things.
first black hole episode.
But man, black holes are just so cool. I remember I explained how when you're going towards a black hole, it starts as a point, and then once you pass the event horizon, like your entire universe is perfectly like 50% black, 50% universe. And then the more like the further you get into a black hole, the more the universe contracts into a single point, and the rest of your universe becomes black. Crazy.
It's bro,
such a
black
crazy
holes itself have a whole. I mean, black hole physics is a thing of itself. It's a field of itself. And Hawking basically, I'm not gonna say invented, but he fueled the invention. Because a big thing that he also did was literally black hole mechanics. That was not a thing. Black hole dynamics, black hole mechanics was not really a thing, and he basically invented it.
Such a
with
scary
thermodynamics.
topic.
I know, like how do you, right? So with thermodynamics, and now we know, and everything like that, he used that to basically apply it to black holes to make laws, like with other scientists. Him and I believe 2 other individuals, they proposed the laws of black hole mechanics for the very first time. So just very, very in-depth into black holes and cosmology. And do remember, at this time, and even now, I mean, not that we know much, but black holes were highly theoretical. The only place that they really existed was on paper.
Yeah.
Right? We hadn't even thought about observing one of these things.
I have a crazy question. And feel free to answer this question if you're listening to this right now. I would be genuinely curious to see like what percentage of the population, probably not a lot, but would you, if you had the option to be like, okay, you get like another 10 years on Earth, but 10 years from now, you have the option to be thrown into a black hole. Would you do it? Like crazy experience.
Why are we? This is
Crazy.
the dumbest question, though. Like,
would you not do it? I would do it.
be thrown into a black hole?
What? That'd be the craziest experience ever.
I guess you're just gonna die immediately. I mean,
Okay,
not
no,
really,
you're
but,
like you're going to die. But first of all, you're gonna be the first person to ever go into a black hole. Second of all, you don't know if you're gonna die. What if there's a tesseract? What if there's the whole time travel thing?
Not a topic of today's discussion, but
I
definitely
know.
a cool.
But
cool
would you?
thought.
Would you? Yes or no?
I mean, you said like I'm already at the end of my life and the kind of thing, and like I'm already dying, so I can.
No, 10 years from now.
Oh, 10 years from now.
From now.
You would do that? 10 years
I would
from
consider it. I would
now?
consider
I would not
it.
do that. No, I want to live my life here on Earth. before
A
just
black
going.
hole though. Like it
Anyways.
includes the trip and like you get to see the universe,
Okay,
you know what I
cool.
mean?
Anyways, point being that Hawking was very crucial in parts of black hole mechanics.
No, for sure.
And because at that time, the Big Bang theory and the steady state theory were the only two ones that were really there. Like steady state being that the universe had always existed and will always exist, right? But the inflationary model had some backing to it, but not many people were convinced, which is when he kind of came up with this mathematical reasoning, posted it as his thesis, and well, now we know.
Thinking the universe is flat and infinite is so like it seems so like simple. Like it's too simple of an answer. Where does the universe come from? It's just literally always been here.
But
And
you have to
doesn't
understand, at that
change.
time, like there are no ways to measure and no ways
No,
to really
I-
think about anything apart from us.
Wait, there wasn't redshift?
Oh, yeah.
Back in
Hubble,
the-
Hubble happened.
Yeah,
happened
Hubble.
before this. No, but steady state also explained that because you can just have individual galaxies moving away. Because remember, like the observations weren't very heavy at that
Yeah.
time.
Yeah.
Like it wasn't like we have catalogs and trillions of stars.
But it still seems like at the time you could just be listening to the scientists say these things and be like, really? We're going
Now,
we're
man,
going with
now. We
we're
can't
going
say
with
that then.
eternal.
We can't say
That's
that
the
then.
answer.
Anyways, that's a little bit of Hawking
Yeah.
and how he started his postdoctorate career. Definitely cooler things, and I think you already know what's coming up. I mean, who
What
doesn't?
about Mr. Gauss?
Let's move on.
I don't
to
think
Gauss.
he's a doctor, to be honest. I don't.
No
think
way.
I mean, this was in the 17s. I don't know. Anyway,
I guess Isaac. Wait, when was the philosophy?
I
even
don't know.
When was Doctor of
when was
Philosophy?
Doctor of Philosophy a thing?
Like, when did it start?
Because
I'm
it
not-
had to start at 19.
No way! No,
that's not true. It's a 1998.
It was
Wait,
when
oh.
was HD invented,
Oh,
not PhD,
oh,
like high
oh, that's
definition.
funny.
The first doctorate degree was granted in the
12th?
12th
Okay.
century, so he could have definitely got one.
Yeah, for sure.
Okay, anyways, continue. Let's hear a little bit about Gauss.
Okay, so he was so smart that the Duke of Brunswick,
Oh.
whatever that means, sent him to college.
Whatever that means. Okay, anyway.
I mean, okay, he's somebody.
Yeah, continue,
whatever.
continue.
He sent him to basically a college / university at the time. This was in 1972. So do note, if I have quick maths right now,
72, you mean.
he was 15 years old.
17.
17.
Yes,
Nice.
you said 19.
Oh, 1792
1792. Okay.
when he was 15.
Mm.
15 years old. Going to
Sounds good.
university. Okay.
He's 15 years old
Okay.
right now. Okay.
And so he went there for a few years, and after that he went to the University of Göttingen. Göttingen. I don't know how to say that, but he went there for another 3 years. So while he was in university, just guess what he did on his free time.
Probably invented something.
He rediscovered important theorems on his own. He was just, you know what?
Wow.
Going from the bare bones and just discovering things that were already known. And yeah, he's a big number theory guy. he likes geometry, shapes, relationships between numbers for some reason. You know what I mean? Like, this number is a square of a power of 2 that is divisible by only 3 primes. So it's a triangular diagonal number. Anyways, that's just me making fun of number theory. So yeah, not many interesting things. I mean, obviously interesting things happened while he was in university, but the gist of it is that he was smart and he made a lot of breakthroughs that don't really seem like breakthroughs because they're just mathematical things. You know what I mean? Like, for example, it said that he showed that a regular polygon can be constructed with a compass and a straight edge if the number of its sides is the product of distinct Fermat primes and a power of 2. That was a breakthrough that in 1796. I don't know the weight behind that breakthrough. Like, is that so important? I don't know. It feels rather specific.
I mean, anything really like based like in that level of
mathematics exactly.
Sounds like it would be really important.
It seems really specific and really like, breakthrough though. I don't know.
I mean, I can see that.
I feel like calculus is a breakthrough. You know?
That is like a revolution. That's not a break. That's like literally changing mathematics.
I mean breakthrough
breakthrough
at a minimum.
Yeah, that's I know, but that's what I'm saying. Like, calculus is such a high level of a breakthrough that I don't even think they're on really the same level.
Yeah, no.
Like, this is probably like a minor breakthrough, like a really.
It says breakthrough. I don't know what you want.
It says breakthrough, but it's a really minor breakthrough.
So okay, let's talk about like the things that he did. You know what I mean? First of all,
Gauss did so many things.
This guy was in algebra. This guy was in astronomy, statistics. Crazy.
So important in statistics.
Magnetism.
So important in magnetism.
Crazy. Okay, so let's talk about a little bit of algebra here. So he wrote a bunch of things. I don't think it's useful to just start naming things that he wrote, so I'm not going to do that. But he did prove some of the following conjectures, which I think is pretty interesting. So at the time, you had a bunch of statements and people didn't know like if they were true. Like, they guessed, they conjectured them, but he proved a whole bunch of them. So first of all, he proved Fermat's polygonal number theorem. I'm not going to go through the proof, but I will tell you what the theorem is. Yeah,
okay. I want to know that.
Okay, so the Fermat polygonal number theorem states that every positive integer is a sum of at most n n-gonal numbers. So what does that mean? So an n-gonal number is not really what you think, but here's what it is. I'll start with an example. Okay. A triangular number is a 3-gonal number. Okay. It's basically, if you can make a triangle with those
like
numbers.
3, 4, 5? Like the 3, 4, 5 triangle?
Yeah. If you can make triangles with that amount of dots, then it's a triangular and 3-gonal number.
So what's the number? Like for 3, 4, 5 for the sides, like what's the number related to?
No, not like that. Not like that. Like you can have 3, and then you can have 3 plus 3, 6, right? Like you just keep adding rows. You have 1, and then 3, and then 6, and then 10, and then 15.
Oh, you're talking about the you're talking about
like cups, you know what I mean?
Yeah. You're talking about what do you call it?
When you build a triangle.
Yeah. Your Pascal's triangle.
Yeah.
Yeah, that's exactly what you're talking about.
That's a 3-gonal number, triangular numbers. And then square numbers is if you can build a square, so 3, 9, 16. And then pentagonal number, you got to build a pentagon. So then, it's weird. But anyways, what this theorem is saying is that any positive integer, just for all positive integer, it's at most, so it's a sum of at most n-gonal numbers. So you can write any integer as you need at most 3 triangular numbers or at most 4 square numbers. 5 pentagonal, you know? That's I feel like the proof for this has to be absolutely crazy.
Oh yeah, for sure.
Because you have to prove this for like, I guess if it can be done with base case and then induction, yeah, that would be kind of cool.
Induction is usually what I was, because anytime you have an n,
yeah,
you can just use induction is what I was thinking too.
But I guess I'm not really well versed in this kind of stuff. But still, it's an interesting interesting theorem that he proved. He also proved Fermat's last theorem, which is actually a very famous theorem. I know there's a great video that Numberphile made about Fermat's last theorem, and Carl Gauss proved it. And so, Fermat's last theorem, it states that there are no 3 positive integers that satisfy the equation a to the n plus b to the n equals c to the n for any integer value of n greater than 2. We're both familiar. I mean, if n is equal to 1, you can find a couple.
I think we can.
You can find a couple. If n is equal to 2, think of Pythagoras, right? Just think of a couple of triangles. If n is equal to 3, though, I think you might be out of luck. And I think for any other number, you also might be out of luck. But it turns out that I'm pretty sure there's a special case where if n is equal to 4, then something weird happens.
Okay.
But
was that the point of the principle, or no? Like when n equals a certain number, something happened.
No, if n is greater than 2,
okay,
then it's not possible.
Oh, then it's not possible.
Yeah, it's just not. You just can't do it.
Oh, that's what you're saying.
Like you can't find 3 positive integers that, raised to the n plus raised to the n equals just an integer raised to the n.
So these are all like very heavily rooted in math, clearly. So he was...
For sure.
Wow.
For sure.
Damn.
Yeah. So those were a couple of theorems that he proved. And I guess now we can switch back to...
Mr. or Dr. Stephen Hawking. Now, the other thing about Hawking, which was really cool, is that he started studying quantum mechanics after his original paper, after his big thesis paper on the black hole dynamics and stuff like that. He
started after that.
Or like he started as in he got into cosmology and like quantum mechanics. And he was a big lover of loop quantum gravity. And he was a big lover of the many worlds interpretation.
Which we both talked about before here on the podcast.
So he was an avid believer of the many worlds interpretation of quantum mechanics. I mean, not that one way is better than the other. Maybe we can say that. Maybe we can say it, but you know what I mean. Like, they're both equally, they have their pros and their cons. One just describing parallel universes at every split moment in reality. One just describing probabilities, right? So, anyways, this guy starts to get into the thermodynamics of a black hole and starts to basically solve for like entropy. Black hole entropy came from Stephen Hawking.
We saw that.
Yeah, I think we did.
We saw that formula.
We did see that. So that comes from Stephen Hawking, that whole understanding of how a black hole can get more disordered over time. And the whole thing with black holes, a big part of black holes that he also answered with this theory, but it wasn't his primary response, but it was a consequence of this, was the information paradox. It's, well, if hypothetically I have an object that is destroying matter, quote unquote, because that's what we believe goes on in black holes.
Still?
Well, not anymore. Hawking, but like that's what I'm trying to say. But so the whole thing with the information paradox is if that information should not be lost. That's the whole point. So if let's say there's a 1 and 0 in the universe, that 1 and 0, no matter where and how molded it is, it should remain a 1 and 0. And even though that might not have made a lot of sense, what I'm trying to say is an object might not retain its physical properties. I mean, it obviously, like after a black hole, it really can't. But the idea is that the net information, that the net material in the universe does not change. So if I give this black hole some matter and it just destroys it, if I think about a logical conclusion, can I just put all the matter in the universe and put it in a black hole and destroy the whole universe?
Isn't that like breaking
No,
conservation
that's what I'm
of energy?
exactly. That's what I'm trying to. That's the point I'm trying to pray. That's what I'm trying to say. That when you're just thinking about like putting like a house into a black hole, you're like, whatever, it's a house. But when you think about putting the whole universe into
But
it,
that's not even possible, though.
of course, I'm just trying to give you an analogy of understanding what information I'm talking
But
about.
why would you think about that?
I'm just talking about. Anyways, man, I'm just talking about materials that would hypothetically go into a black hole.
Wait, so are you saying that there's a limited amount of things that you can put in a black hole?
The information paradox is that if you do happen to put information in, it doesn't come out. So the paradox is, well, where is it? So Hawking comes out with this theory, and we all know where this is going in. It's going to Hawking radiation, of course. So now this wasn't only him. I mean, in all scientific papers, we should always be mentioning this every single time. It's always with other people. It's never by themselves. But obviously, like, his name is the primary researcher, stuff like that. So he goes on there. And he was really interested in cosmology, because obviously, but more importantly, this time, quantum mechanics. So he now tries to tie in quantum cosmology for the very first time. So he starts to study like particles, or theoretically, of course, like what would happen to particles outside of black holes. And the whole idea of Hawking radiation, again, I believe we spoke about this in the black hole episode, but just because I'm talking about Hawking, I have to talk about this anyways. Yeah. So the base idea is that a quantum phenomenon known as quantum fluctuations occur at every given moment of time in every single position of space, hypothetically speaking. These are virtual particles that are simply being created and destroyed by the universe.
Hypothetically speaking, or literally speaking?
It actually happens, but I'm saying it doesn't happen every single way and every single time. I'm just saying it always happens.
Yeah.
And so hypothetically was a wrong word, theoretically, and it does happen actually. But
so not hypothetically.
So literally, actually. So literally, these particles are being created everywhere. They're not actual particles, so they don't hold actual mass. They are simply virtual particles. So they're kind of being created just temporarily, just to exist, and then it gets destroyed. Now, you might be wondering, how is that even possible? Search up the Heisenberg uncertainty principle. The energy-time uncertainty principle basically allows for quantum fluctuations to occur. It basically states with uncertainty in energy, you'll have an uncertainty in time. And this virtual particle system represents an uncertainty in energy. So at any given time, if there is this particle system that just appears out of nowhere, it will have a limited amount of time, which is the uncertainty in time, how much ever the uncertainty is, to give back that energy. The more energy it takes, the faster it has to give it back. And that's basically the whole idea that you have to get into before understanding what Hawking radiation really is. So this is what's called quantum fluctuations. Occur everywhere, at all points in space. Now, Hawking does a little bit of thinking. He's like, let's say that this making of this virtual particles, that's called, there's no way. No, particle annihilation and particle... No, there's no way I'm forgetting this.
Defilation.
No, there's no way I'm forgetting this. No, there's no way. No, there's no way I'm forgetting this right now.
Creation.
Particle annihilation is when they destroy each other. And particle... Damn it. Anyways, there's something where they get formed. Shoot, I feel really stupid for forgetting this. And I know this. And I'm going to watch this and feel so stupid because I'm going to figure it out then. But anyways, so these particles get formed in some phenomenon. And it's called something. And in this process, he said, what if this happens at the edge of a black hole? So hypothetically speaking, because these fluctuations happen supposedly at all points in time, at all points in space. So if it's happening at the edge of a black hole, well, what would theoretically happen? So Hawking proposes, well, the whole idea of a black hole is that once you're in, you can't get out. So because that's technically still a part of the position spectrum of the universe, if a particle just gets popped in there, if one of the virtual particles pops into the black hole and the other one is on the outside, which simply by laws of probability, if it happens everywhere at all time, it should happen there, right? Simply by statistics, you can kind of understand that it should happen there. So by that, what he basically says is one of those particles can't escape anymore because they have now been tied in to the black hole. Now, this is also a kind of a continuation of the information paradox. This is also saying you've been provided a virtual system, and you have now provided the universe with more information than it first had. How is this possible? And this is his response. He basically says that in the process of this particle going inside the black hole, the other particle that's on the outside must balance. Basically, if this particle that's going inside is now no longer connected or can no longer annihilate with the other particle, just logically speaking, I mean, clearly the energy is now no longer going back to the universe. So somehow, temporarily, Heisenberg has been broken, ? Obviously not, but that's the whole idea. Where is this particle system going? What is it really doing? You know, if it can't annihilate anymore, that means energy has somehow been, conservation of energy has been broken. So what the theory that he came up with, and this is all very, very mathematical. For me to convince you might be a little hard, but it's all very, very, very mathematical, and it's all there. And he basically states that, hey, this guy that comes out, this particle that comes out, to balance the energy that's lost in the universe, it gains mass. So what you just heard from me is that a virtual particle becomes a real particle.
Whoa.
Yeah.
I didn't know that.
And this happens at the edge of the event horizon.
And it happens as soon as the other one enters the black hole?
As soon as the other one enters the black hole, this particle must gain mass for the law of conservation of energy to work. For the law of conservation of energy to work. And this particle that's now being emitted basically has come out of literally nowhere, because where did that come from? And the answer to the information paradox for, if I put something in, why is it coming out? How is it not coming out? Is that it's the information or the matter in our universe is still balanced, because equally that goes in, equally comes out. Now, how does that work? Very interesting question. Mass. The more that you put in, the more has to come out. And that's with the virtual particle system, right? In a black hole, if you ever supply it with more mass, you wouldn't think that it has to give more mass away, right? Like it would just retain that more mass. Like you keep supplying, it'll just go bigger and bigger. But what's actually happening, and it just takes a long time, so you don't really see, what's actually happening is the moment you give the black hole more mass, it's evaporating faster. You just don't notice it, but it's actually evaporating faster.
But, okay, hold on.
Or not faster, sorry. Faster is the wrong term, because smaller black holes evaporate faster than larger black holes. It's all I'm saying is the mass of the black hole simply dictates the amount of, like, the radiation coming out of it. And these particles is now deemed as Hawking radiation.
Wait, does this have to do with the size of the event horizon? Because the bigger the event horizon, the more surface area there is
for this to happen.
To have these events happening.
But because these events happen everywhere uniformly through space.
But if compared to a small black hole and a huge black hole, like there's just more.
But proportion.
Exactly. No, but what I'm saying is that bigger black holes.
But density would probably be the same, no? Like the density of those virtual particles, right? Just because it's a bigger volume, bigger.
Yeah, but I'm saying more events happening.
Because I know for a fact that with microscope, like the whole theory behind this is, well, you lose mass faster the smaller you get. Because like microscopic black holes will evaporate instantly because of Hawking radiation. Because as these particles it'll literally just rip apart the black hole and it'll just evaporate. And a big part of this is also like how black holes die, right? Or not die is the wrong word, but how they kind of, the end of their black hole's life is basically Hawking radiation, right? And understanding that, hey, this black hole is actively giving out this radiation that we to date have not been able to measure, obviously, because this stuff is really, really far away. But it's all been theorized, and it does match up with what we have with general relativity, because that's how this started in the first place. So it kind of makes sense from where he's coming from. It does answer a lot of questions that we did have with black holes originally. It's also I just thought of something that I forgot that I may mention again later, but he does come into play a lot when it comes to just understanding the thermodynamics of black holes, because again, at the end of the day, this is like radiation being emitted almost. And again, like, we haven't actually experimented on these things, but if we do, it should make sense, because another theory that also kind of goes with this is primordial black holes. So primordial black holes, which are original OG black holes, we should be able to see if they're over a certain amount of mass by Hawking radiation. And if they're under a certain amount of mass, we should not be able to see them, because Hawking radiation should have taken that all away. We haven't been able to see any discrepancies in it, so far it's good. You know what I mean? So primordial black holes at least also do, I mean, we haven't actually noticed anything yet, but any, deviation from what we already understand would give us something into understanding what Hawking was trying to say. But so far, just how black holes basically evaporate themselves. And again, the first time that Hawking went a little bit into quantum mechanics, which was really cool.
Very fruitful.
Very, very fruitful indeed. Again, him being called Einstein now seems kind of funny because quantum mechanics and everything. But yeah. So that's basically Hawking. Those are like two of his. Am I forgetting anything? I don't think so. Those are two of his biggest things. I mean, he's always wanted. It's always cool. Like he always wanted to go to space, and he did. Right?
Really?
Yeah, he did. He did. Like Wait, am I forgetting? I swear he went in the parabolic plane. Did he not?
I don't think that counts as space.
No, but that was his weightlessness, man.
Yeah,
Like
okay.
weightlessness. That was his whole thing.
I don't think that counts as space.
Anyways, Hawking was a really cool guy. It would have been awesome. Imagine if he was on the podcast.
He came to U of T.
He did come to U of
He
T.
came to U of T.
Literally, didn't Matt see him?
No.
I swear.
No.
I know someone that saw him.
He came in like the 80s or the 90s or something.
Okay, then I'm completely tripping. I thought someone saw him recently. Never mind.
No.
I thought he came 10, 20 years back, and I know of a TA, not Matt, sorry. Maybe a TA or something that saw him, but I could be mistaken. Anyways, that's Stephen Hawking for you.
So yeah.
A little bit of that, a little bit of this.
Now on to one of the things that dictates your entire life.
Oh.
Your entire existence is dictated by this piece of mathematics.
Yep.
The normal distribution.
The normal distribution.
Dumb. So basically, let me put it into basic terms. Everything you've ever done or said or was a product of you being alive follows a normal distribution.
That's crazy.
Listen, your height fits perfectly in a normal distribution of a histogram of every human's height ever.
Yeah, I thought you were gonna say your height, because your height is
like
not
you like
uniform at all.
adding like your data point
Oh yeah,
contributes
That's what you're trying to
contributes
say.
to a perfect fit of
Like if you create a histogram on the heights of every person in the world,
Yep.
it will basically create something that looks normal.
Mm-hmm.
Now, what is normal?
Now,
I don't know
okay.
if everyone's seen a normal
So-
graph before.
Listen, a bell curve.
Bell curve.
Okay. Something that makes me think a lot is that in high school, when we were learning about bell curves, I was always wondering, like, why is that the formula for a bell curve? You know what I mean?
Like the
What-
complicated exponential.
Yeah, like why can't I just pick, like, why can't I do pi to the minus x squared? It's just different, you know?
No, there's a reason though.
No, there's a reason for sure.
Okay.
So let's talk about, first of all, a bell curve. So a bell
Mhm.
curve, we've all seen one. It's this thing, it goes to 0 at infinity, and then it looks like a bell. There's a nice mean, it's symmetrical, which is, a beautiful property.
Property of it. Yeah.
There's, the mean and the median and all that stuff is all in one place. And the best thing about the bell curve is that, well, it's an equation. It has a mean value, which you can put anywhere, and it also has a standard deviation, which just tells you the width of the curve, which actually caused so much confusion for me in high school. I would ask my math teacher. He wasn't even teaching me statistics, but I went to him for him to explain this to me. And even his explanation wasn't even good for my brain to understand. He's like, yeah, it's the width. I'm like, what do you mean the width? The width always changes. He's like, it's just a number that tells you the width. And I'm like, I don't really get that, to be honest. Because to me, the width is like, if it was a constant width, then that would make sense.
Yeah,
but
but it always changes.
The width always changes
depending
on where you are. So didn't really make. Now I get it though. Now I got a solid grip on that. But it just tells you how far, in general, the distribution goes away from the mean. So if your standard deviation is very small, it'll be like a spike. Most of your data points. Should I be saying data points right now?
Data is, I mean, that is mostly where we use normal. So I think people can kind of relate to it.
When I say data points, I kind of mean area under the curve. Speaking of area under the curve, the area under the curve is 1. It's normal. It was defined to be normalized.
Well, yeah,
though.
that's how you.
But this, like the bell curve that we usually use, the normal distribution is if you're not taking into consideration like the standard deviation, so just a unit normal distribution is 1 over root pi, which is just the normalization constant, and then times e to the minus x squared. Why is this such a cool function? And notice that if you have a function that goes to 0, or I guess you could say the improper integral converges, you can find a finite number for the area under your function. And to normalize that function just means that you take the integral from minus infinity to infinity, or wherever the domain of your function is, and you divide it by that value. So automatically, as you know, you can take out constants from integrals. So if you were to integrate the function that you just divided by the integral, you could take that out, and then you just get the value of the integral divided by the value of the integral. So by definition, you get a value of 1. And normalization is beautiful because in quantum mechanics, we deal with a lot of normalization, especially in statistics. You know, quantum mechanics is like a subfield of statistics. And whenever you're dealing with probability density, amplitude, everything is just so much better and makes, not even so much better, just makes sense when you normalize it. If you don't normalize something, it doesn't mean anything.
But it depends on what you're normalizing. I mean, obviously, when it comes to any type of distribution, you have probabilities.
No, you have to.
If you don't normalize it, that literally
it doesn't mean
means
anything.
Like it literally means absolutely squat if you don't normalize a probability function. And Gauss, I mean, the bell curve itself is literally, I mean, obviously I can pop off on it for statistics, but like I'm just saying that when it comes just to understanding, well, probabilities, what's most likely to happen. I think I've spoken about this in an episode where, like, and you just said it, your whole life is dictated by a normal distribution. You will get really lucky sometimes. You'll have some really bad days, but on average, you'll have a decent day.
For sure.
Unless your average is just terrible. You know, that's just sad. I feel bad for you. But anyways, the normal is really powerful also for another reason. Because
I was going to say something cool.
Okay, no, continue. Okay. No, continue.
No, I was going to say something cool because I was talking about normalization.
Yeah. Continue.
So you might ask yourself, how do you normalize a bell curve? If I give you e to the minus x squared, how do you do that? Now, here's a quote from our calculus professor that we had on the podcast, I think episode number 4 or 5. Mihai. Anyways.
Oh, Mihai. That was like, that was not 4 for sure.
The episode was called Math We Can't Understand.
Yeah, that was such a good episode. That was such a good episode. We really had no idea what he was saying. He was like talking about like Lie algebra and all this crazy stuff. Like obviously it was interesting, but
no, it was definitely interesting.
Super cool. But yeah.
But when we were dealing with when did we talk about this integral, the Gaussian integral in first year?
We didn't.
No, we did.
Not in class.
In class, for sure. And here's what Mihai said. Mihai said, everybody try this integral. If you can solve it, if you can solve this integral, I will eat my backpack.
That's what he said.
He said that, and I made me laugh so hard.
That was
Because
so
I was
funny.
like, all right, let me
I'm just like, it's obviously just not
let
possible.
me try this. No, it was not possible. Well, not possible with elementary
Thinking.
no, like
You get Gauss in there, bro. Come on. He would have eaten his backpack.
No, for sure. But I mean elementary integral solving techniques. You can't do any type of substitution or anything like that for this integral. But just here's a little outline of how when you do go into more general calculus, for example, multivariable calculus is a little bit more general. You can actually use ideas from multivariable calculus in order to solve this integral. And here's just the general outline. You have the integral. If you multiply that integral by itself, the variable that you're integrating over is just a dummy variable. So you can call one of them x. The first one is over x. The second one is over y. But since you're just multiplying the same integral by itself, it's just that integral squared, right? So now you're solving the square of the Gaussian integral all over infinity. And it's equal to, now you have two dummy variables, but when you're multiplying these like beautiful continuous functions, that means you can just make it into a double integral. And now your power is very beautiful because you can turn it into a polar coordinate situation, and then it becomes really easy. If you were to see it with your eyes, you'd believe me. And then now you have the answer, but that's the square of your function, the square of your integral. So you just square root that function. Turns out the answer is pi to the square, and which means that the answer to the original one is root pi, which, how fitting. You have e to the minus x squared. Of course, the integral over infinity of that integral is square root of pi.
Like, what do e and pi, like, fundamentally have to do it? Like, they have nothing, really.
Nope.
Like, pi is just completely separate. E is, like, compounding interest. And what?
Yeah, the first, like, could you imagine that integral being equal to 2? Like, no way. It had to be something like root pi.
It's so funny.
It had to be something like root pi.
No, it had to be something complicated. But I'm just saying, it's just so interesting that, like, the world has to work in this weird way.
Yeah.
That's a weird integral that
Definitely.
he solved.
Now, listen, I wanted to talk about electromagnetism.
Oh, he was a big part in that, yeah.
I do think due to time constraints, we might have to end the episode right here. I know. But yeah, it is getting pretty late.
Yeah, we do. That's the only
Yeah.
thing. Like, we really do want to talk more. But, man, like, as we said, like, we've already delayed it a day. Like, we just have so much stuff to do. I know you have a lot of stuff. I have a midterm coming up soon. So we just have, it's just work at the end of the day. I mean, I guess, okay, fudge cake. Kind of wanted to talk.
Yeah.
Also, one thing I did want to mention is that the black hole thing that I was mentioning is kind of a little different. So the information paradox is still the same, that, hey, whatever you put in doesn't come out. But while I was saying it, I was thinking, because the whole point of the information paradox is to, like, give back the information that you put in. But this has nothing to do with the information that you put in. Like, these particles that are coming out have nothing to do with what you put in. So that's, like, what I was thinking for while I was saying it. And after a quick Google search, so Hawking's theory actually started the information paradox because it evaporates this thing and this black hole will one day get to nothing. The question is, where does the information go? So that's actually how it's kind of started and not the answer to it. So that's kind of interesting. And a lot of the thermal radiation currently is actually also provided by Planck's radiation law. So that is currently where we believe the information is coming out from, simply by thermal radiation. So the Hawking radiation should explain a small amount of literal light that we should be seeing that's reflected from these particles. So we should be seeing, like, a light around the event horizon. And again, we haven't actually done anything that's that crazy, but I mean, who knows, right? Who knows? Anyways, crazy individual. I mean, Gauss is too. Definitely could have popped off on the electromagnetism part of Gauss.
We can continue this a little bit.
We always have a next time, because I
later.
think Gauss, we can do an episode on Gauss, man.
Yeah.
I mean, we can really do an episode on any one of these physicists, but we're just here to summarize what they did for you.
Well, thank you for listening to this episode of
As
the
always.
podcast.
As always.
This has been number 84. Please make sure to follow wherever you're listening to this. Let's get to 21,000 followers before New Year's.
21,000? I hear you, Parker. I hear you.
Let's get to
21.
21,000.
That would be pretty lit.
But
I really want to. Okay, I don't know how possible this is because I've like not been looking at the numbers at all. But 2,000 YouTube by December. What do you think?
yeah.
Possible?
No,
2,000 subscribers.
For sure.
I think we can do it.
All right.
I think we can do it. Just go hit that subscribe icon. Like the video. Comment as always. We love to. Man, you have to understand how much we read the comments, but we just don't have time to reply to all of them. We definitely. I love to read. I've read every single comment that has popped up. So if you guys are commenting and be like, oh, he's not going to. No, we read. We both read them diligently. It's just that we don't always have the time to respond to some of them, especially when some of them are kind of like long where we want to think about a response. So keep them coming. We love it as always. Comment down for the comment of the week for next episode. And anything else?
This has been episode number 84 of the
It
Math
has.
and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we'll see you soon.
Bye, guys.
See ya.